So then, although many of you already know Juan very well, so that he needs no introduction, but let me just, oh, he left. Let me mention that Juan is a pleasure to have Juan with us, who is going to talk about the entropy of Hawking radiation, a very interesting subject. And then Juan is a Carl Feinberg professor at the Institute for Advanced Studies in Princeton. You probably don't know, but he was born in Buenos Aires back in 1968. So 6 years after my birth at the same place. So he graduated from the Instituto Balseiro in Argentina in 1991, also 6 years after I graduated from the same place. But then he moved to the US, and he received a PhD from Princeton University in 1996. He was then a professor at Harvard before joining the Institute in 2001. As you probably well know, his research interests include quantum field theory, quantum gravity, and string theory, and he has been particularly interested in the relationship between quantum systems and gravity. And you are probably aware of the ADSC-CFT correspondence conjecture that he proposed some years ago. So he is a member of the National Academy of Sciences, the American Academy of Arts and Sciences, the Third World Academy of Science, and many other places. And his awards include the Danny Heinemann Prize, the Dirac Prize, the Einstein Medal, the MacArthur Fellowship, and the Fundamental Prize. Then, and with no further introduction, I believe we should leave Juan explaining us something about the entropy of Hawking radiation.
Okay, thank you for the kind introduction. Can you see my screen? And can you hear me? Yeah. Okay. So we'll be talking about the entropy of Hawking radiation. As you know, black holes have been in the news in recent years. Gravity waves, the Event Horizon Telescope, and most recently, the black hole in the center of the Milky Way. And we'll also talk about black holes, but we will really talk about quantum aspects of black holes. These quantum aspects are not very important for these astrophysical black holes, but they are very conceptually important for understanding the relationship between quantum mechanics and gravity. And more in particular, we will discuss recent progress on the black hole information problem. So the outline of the talk is roughly the following. So I'll remind you that the entropy of a black hole is related to the area of the horizon. And then we'll talk about a formula for the fine-grained gravitational entropy. And we'll say that the entropy is equal also to an area. It's a so-called minimal area. We'll see in detail what that means. And then we will use these formulas to compute the entropy of radiation coming out of black holes. And the main message is that we get a result that is consistent with information conservation as opposed to information loss. Now, this talk will not be historical, but hopefully it will be pedagogical. So the story about black holes starts with the famous Schwarzschild metric, which is written here. This metric describes the outside geometry of a black hole. As you see the two-dimensional sphere, the radial direction, the time direction, and so on. Now, an interesting result is that when you include the effects of quantum mechanics, black holes have a temperature which is inversely proportional to the size of the horizon. So the horizon, if we go back, let me go back. So here we see that there is a place where the time component of the metric shrinks to 0. That defines the position of the horizon and is given in terms of the mass by this formula. Okay, so now let me try to explain. So I'll give here an argument for why that is the temperature of a black hole. And it's a slightly abstract argument, but it's sort of a quick argument. So first, let me remind you that if you compute the thermal partition function of a quantum system, or a classical system, you sum over all states the quantity which is e to the minus beta h. So you're computing the canonical partition function of the system. Now, this particular trace of the Hamiltonian, of e to the minus beta times the Hamiltonian, is equivalent to evolving the system on a circle in Euclidean time of length beta. The reason is that if we put, instead of beta, we had here I times t, that would be the ordinary time evolution. But if we make t imaginary, then we have equal to beta, then we have this factor of beta here. And the trace is essentially similar to saying that we have the system on a circle. So we sum over all the states propagating on that Euclidean circle. So in other words, if we consider a theory on a Euclidean time, so you take any quantum system, let's say a harmonic oscillator, and you put it on a circle in Euclidean time, then that problem is telling you something about the system in thermal equilibrium. At the temperature, which is inversely proportional to beta, well, of course, that's inverse, beta is the inverse temperature, and that's 1 over the size of the Euclidean circle. So now we go back to the black hole. So the first line here is the ordinary Lorentzian metric, the one that Schwarzschild had. And here we say, well, let's make time imaginary. So if we make time imaginary, we get a minus sign, so we get the metric which is purely Euclidean. And this metric again shrinks to 0 at this position of the horizon. But if we make the time direction a circle with the appropriate radius, then it will shrink to 0 in a completely smooth way. Okay, and that radius of the circle, which makes the metric completely smooth, is given by 2 pi rs, so that you get by analyzing this metric near the horizon. And with that condition, we get a smooth metric. And we think that this describes a black hole in thermal equilibrium with a bath at a temperature which is inversely proportional to this. And this is, of course, the famous Hawking formula for the temperature. And this was a derivation that was given by Gibbons and Hawking. Now, that result for the temperature implies a certain result for the entropy. And you get that result from the entropy by integrating the first law of thermodynamics. This is roughly the same, following the same procedure that an experimentalist in the lab could follow, but when presented with some new material, you could measure the specific heat, see how the temperature moves, and integrate the change in energy versus the temperature. And then you get a formula for the entropy that you obtain by using the known formula for the mass as a function of the radius and the known formula for the temperature. That gives you a formula for the entropy, which turns out to be the area of the horizon divided by 4 times g Newton. So this is in units where the Boltzmann constant and h bar and c are 1. That's the same as the area divided by 4 L Planck squared. L Planck is 10 to the minus 33 centimeters. So for a macroscopic black hole, this is a huge entropy. So the fact that the black hole is a thermodynamic object is, of course, surprising. But we will discuss now in more detail the geometry of a black hole. So first, we discuss the geometry of a black hole made from collapse. So what we discussed so far has more to do with black holes in thermal equilibrium. So now we consider a black hole from collapse. So we have, and in order to describe black holes, it's convenient to use certain diagrams that were introduced by Penrose, well, Penrose and Carter. Penrose was the person who got the Nobel Prize this year for his work on black holes, together with observers, astrophysicists. So These diagrams work as follows. So each point on this diagram represents a point in the time and radial directions. And on each point, we have a two-dimensional sphere, which is the sphere around the black hole at that point. So we're using the spherical symmetry of the black hole, so we're not going to talk about the sphere. The vertical direction is roughly time, and the horizontal direction is roughly the radial direction, but they've been compressed so that they fit in this diagram, and they've been compressed by rescaling that preserves the direction of light rays. So light rays propagate at 45 degrees in these diagrams. So the surface R equal to Rs, or the horizon that we talked about before, corresponds to actually this whole one-dimensional surface here in this diagram. And it's really three-dimensional because there is a two-sphere. The Schwarzschild metric that we discussed describes the black hole exterior. Of course, in the interior, we'll have a different metric because we have the matter of the star that causes some deformations in the geometry. Then in the future, in the interior, we have a singularity. So the space-time collapses here in a kind of big crunch, and we have the singularity of the black hole is represented here. Here, far away, we have the region very far away from the black hole. So this is space which looks like flat space far away. So that's the geometry of a black hole made from collapse. Important point is that if you are in the interior and you try to go outside, the fastest you can go outside is following a line of 45 degrees at the speed of light. And even if you go at that speed, you will end up at the singularity. You just cannot escape outside. Only if you are outside the horizon, you can escape to infinity. So space-time is divided into two regions: the region where you can escape to infinity outside the horizon, and the region where you inevitably will fall into a singularity, which is here in the black hole interior. Now, it turns out that general relativity implies that the area of a black hole horizon always increases. And this is some mathematical theorem you can derive from the equations, from Einstein's equations, the classical equations of Einstein. And it turns out that this, you could reinterpret it as the second law of thermodynamics, saying that the entropy increases. So the area of the horizon starts being zero at this point, because this is this vertical direction, I didn't say it, but this vertical direction here is like the origin of coordinates, so r equal to 0. Here, the two spheres shrink in a smooth way. And when the black hole forms, so the horizon comes out, and the area starts increasing until it reaches the maximum here, and then it stays constant. I should emphasize that the horizon is not really a physical surface. It's just some imaginary surface that separates two regions of the space-time. So it's present in our description, but an observer who's falling here with the star or is falling into the black hole doesn't notice anything peculiar when crossing the horizon. Now, it's useful to, so if you, I should mention this. So it turns out that the full entropy of the black hole is not just the area of the horizon, but also we should include the matter that is outside the horizon. So, so that's what gives us the full entropy of a black hole system. So if we have some matter at finite temperature, we should include that entropy. Now, we can ask a question. So when the black hole emits Hawking radiation, so it's at some temperature and it will emit radiation, and it will lose energy. So as it loses energy, its mass becomes smaller, and that in turn will imply the area of the horizon will become smaller. And so the question is, what happens to the entropy? Now, it turns out that in this formula where we talk about the entropy of matter, we should also include the entropy of quantum fields. So the entropy of the quantum fields in the vacuum. Now, naively, you would think that the quantum fields don't carry any entropy, and that's correct if you think about the full vacuum state of everywhere in space. But if you divide space into two parts, the part that is outside the horizon from the part that is inside the horizon, then that same vacuum, when restricted only to the outside, will have some non-trivial entropy that comes from quantum mechanics, and is related to the entanglement of the quantum fields between the outside and the inside of the black hole. This is essentially the same as saying that the Hawking radiation contributes to the matter entropy. And so this whole quantity actually increases in the process of black hole evaporation. So the area term decreases, but the entropy of Hawking radiation increases by a higher amount. Actually, it increases more than these decreases. So in fact, it obeys the second law. And it's only very recently that the second law was proven, including all the quantum corrections by Aaron Wall in 2010. Now, these various results implied a central hypothesis in the study of quantum aspects of black holes. And it's the idea that black holes can be viewed as quantum systems. So if you consider a black hole and you stay outside the black hole, you stay safely outside the black hole, then you can describe all the interactions of matter with the black hole, both the matter that falls in and the Hawking radiation that comes out. All of that can be described in terms of a quantum system with S degrees of freedom, or S qubits, let's say, or Majorana fermions, where S is the area of the horizon in Planck units. And not only that, but it also evolves according to unitary evolution, as seen from the outside. So in pictures, we can replace the black hole by some very complicated system of strongly interacting quantum bits and so on. And that describes, in principle, any measurement that you can do about the black hole as seen from the outside. Now, in other words, if we include these mysterious qubits, then the black hole can be described as an ordinary quantum system. And in further pictures that we'll draw later, we'll say that what we replace is not only the black hole, but the black hole and its atmosphere, so the region near the black hole. So let's say we can take the space-time and we draw some imaginary surface around the black hole, and everything that is in here is replaced by a quantum system. Okay. Of course, this then can interact with the outside and so on. Now, what's the evidence for this, besides those thermodynamic formulas that we saw? Well, in certain theories, in string theory, for example, some special black holes can be counted precisely using strings and D-branes in such a way that we reproduce the area formula. By counted, what we mean is that we can set up a Hilbert space for the theory, and we can count the number of states with those given charges, those given masses, and reproduce the area formula from the statistical formulas, the logarithm of the number of states of that quantum system. And there are various tricks to do this computation, and it's been done with increasing precision for those special black holes. And not only you get the area formula, but also the corrections to the formula that come, for example, from the entropy of quantum fields outside the black hole. Another piece of evidence is the so-called ADS-CFT, which says that if you have a theory in a special curved space called anti-Sitter space, you can replace anything inside the space by a theory of strongly interacting particles on the boundary. And with that picture, the black hole becomes a fluid of strongly interacting particles near the living at the boundary or far away in this space. And this fluid evolves unitarily. Now, all this is very nice. So this is evidence for this central hypothesis. But there is also sort of counter evidence. This was argued in 1976 by Hawking that he said this cannot possibly be true. So he argued against this, what we were calling the fundamental hypothesis. And his argument comes from looking at the geometry of an evaporating black hole that is made from collapse, so same geometry we discussed before. But you now account the effects of Hawking radiation. So this diagram, this Penrose diagram, is slightly different than the one we saw before. So here we include the fact that we create pairs of particles. These are the entangled particles between the outside and the inside of the horizon. The outside particles go to infinity and extract some energy from the black hole. And so the black hole, as we go along the horizon, slowly the mass slowly decreases and eventually at this point evaporates completely. We assume that nothing too drastic happens here at this very endpoint, and then we're left with flat space. So this top part of the diagram is just the diagram of flat space, flat Minkowski space. Now, what Hawking said is, well, here we form the black hole from, let's say, an almost pure state, and then here in the future, we get this radiation, but this radiation is not in a pure quantum state. This radiation is entangled with this radiation, which is inside the black hole. So initially, the two together are in a pure quantum state, but the radiation is now entangled with a system here that is lost at the singularity and is not accessible to the outside observer. Therefore, this outside observer should say that the entropy has increased. And that's incompatible with replacing the whole black hole by a quantum system, because if we excite a quantum system that starts in a pure state and then it decays, initially you can perhaps produce some entropy, but eventually the final state after the state settles down to the ground state should become pure. The state of radiation should become pure. Now, in other words, so here we're doing the same type of calculation. So we start with a pure state that we collapse into a black hole and we watch it evaporate for a while. And we get a curve according to Hawking as we start getting Hawking radiation out, and its entropy starts increasing as we get more and more radiation, and it increases until the black hole evaporates completely and we get some non-zero large entropy at the very end. On the other hand, the thermodynamic entropy of the black hole started large and then it decreases. And we really are getting a contradiction at this particular time. So initially there is no problem with the Hawking radiation having some entropy, because it could be that the Hawking radiation is entangled with the degrees of freedom that describe the black hole. However, when the entropy of Hawking radiation becomes equal to the entropy, thermodynamic entropy of the black hole, then it's would be, let's say, maximally entangled. But after that, the entropy of the Hawking radiation becomes larger than the entropy of the black hole. And then this entropy cannot come from entanglement with the black hole, because the entropy of the black hole is smaller. Okay. So you have a contradiction already at this time. You don't have to wait for the black hole to evaporate completely. And for that reason, we have a contradiction independently of the details of the endpoint of black hole evaporation. So we have a contradiction with the central hypothesis at some intermediate times where the black hole is still big. This is just a qualitative aspect of the curves. The actual curves bend a little bit and so on, depending on the details of the black hole. So what Page said is that if this central hypothesis was correct, then the entropy of radiation should follow this purple curve instead. So it can increase in the beginning, but at this time, this particular time when these two curves cross, the entropy of radiation should start coming down. And the question is, how does it come down? And yeah, how do you see that from the gravity picture? What changes in the gravity theory that makes this entropy come down? So that's what's expected if the system was following unitary evolution. Now, there were other apparent paradoxes with the black hole entropy formula. So this was one of them, but there were a couple of others, and I'll discuss a couple of others now also. One other paradox, apparent problem, was the full Schwarzschild solution. So when you take the Schwarzschild solution describes the exterior of a black hole, but you can analytically continue it. And what you find is that there is an interior region and also there's a second exterior region. So a full metric describes not one black hole, but two black holes. And the question is, what is this and what entropy is this computing? There is a related type of configuration, which is related to the previous one. So here we have two black holes that are joined through the interior. And one, they're both in they're both in Minkowski space. We have two separate Minkowski space, each of which contains a black hole and they're joined through their interiors. You can replace one of the Minkowski spaces by a closed universe, and an initial slice for this geometry will look like this. So we have a closed universe which has a spatial slice which is a 3-sphere, let's say, and is joined with a narrow neck or an Einstein-Rosen bridge to an exterior. We can have a huge amount of entropy inside this region, which is bigger than the area of this neck. Okay. Now this full configuration, when you evolve it in time, will create 2 separate black holes. And you can say, well, from the point of view of this of the outside, you might have thought that the entropy counts the area bounds the entropy inside this region, but the entropy inside this region could be much bigger. So this configuration is a counterexample to the statement that the area counts the entropy inside. And this is known for a long time. Wheeler, I think, was the first one who pointed this out. So now we'll see how to resolve some of these confusions. And these confusions they all involve the black hole interior. And some of them involve the computation of the fine-grained entropy, not the thermodynamic entropy. And these confusions also involve entanglement in some way. So we'll discuss these notions in more detail in order to understand the solutions. So first, let's go a little back to basics. So we had this hypothesis of black holes as quantum systems. It's important that this hypothesis only talks about the black hole as seen from the outside. It's only a statement about the black hole as seen from the outside, and no statement has been made about the interior. Okay, so we'll make a statement about the interior later, and that is related to the recent progress on this subject. So first, let's look at this full Schwarzschild solution, which is a kind of wormhole, so connecting two space-times. So you can put the 2 black holes in the same space-time, but separated by a long distance. And then the geometry near this region would be similar to the geometry we had in the previous page. And this type of geometry, the idea is that it's the same. We apply this central hypothesis to each black hole separately. So we have 2 quantum systems. And the fact that they are connected is related to the fact that they're entangled in a special state. The special state is a state that is sometimes called the thermophile double. This is a state that is useful for, people found it useful for doing calculations in general quantum theories. But it's a peculiar state where you take 2 copies of your quantum system and you take all the energy levels of the system. So you take 2 identical copies. So we have the energy levels of each of the systems, and you sum them in a correlated way with a factor which looks very similar to the thermal factor. So the fact that it looks close to the thermal factor is related to the fact that this is called the thermophile double. So the idea is that then these connected geometries are the same as these entangled states. Now the rest of the paradoxes involved understanding better the so-called fine-grained entropy. Now for this, it's important that we normally think about, we can define 2 notions of entropy. So one is the thermodynamic entropy that obeys the second law of thermodynamics. And it somehow arises from sloppiness. So you might have a system in a pure state, but if you only measure a few variables, then you would assign it a thermodynamic entropy, which is the usual entropy we use in thermodynamics. On the other hand, we also have the fine-grained entropy or von Neumann entropy. This entropy remains constant under unitary time evolution, and it's also sometimes called entanglement entropy or quantum entropy. So you have the density matrix of a quantum system. You take the trace of rho log rho, and that's by definition the quantum entropy. And it really measures the true quantum information content of the system, or if you wish, your ignorance about the system. Now there are some circumstances where these 2 are equal, and sometimes you might not have made the distinction, but for this problem, it's important to make the distinction. For the moment, we'll be talking about the entropy of the black hole as seen from the outside. So the entropy we will compute is the entropy of that quantum system that is supposed to describe the black hole as seen from the outside. The entropy appearing in the quantum system that appeared in the central hypothesis. Now, the horizon area, if it's computing one of these 2 entropies, is computing the thermodynamic entropy. And the reason is that when a black hole forms, this entropy we've seen grows, and the black hole can be forming isolated from the rest of the universe or relatively quickly. And that can only happen, so this large increase in the entropy can only happen for the thermodynamic entropy. The quantum entropy cannot increase under isolated evolution. So the question is, how do we compute that fine-grained entropy? Now, in general, quantum systems is very difficult to calculate this fine-grained entropy. So the normal notions of entropy that we deal with physics, like the entropy you use in hydrodynamics and so on, is usually the thermodynamic entropy. So the fine-grained entropy apparently requires some details about the system, but surprisingly, for these gravitational systems, there is actually a formula for the fine-grained gravitational entropy. So it's a formula that was initially found, a version of this formula was initially found by Ryu and Takayanagi, and then it was improved by various authors. And we'll here discuss just the final form of the formula. It involves a combination that is similar to the combination that computes the thermodynamic entropy. So it's the area of some surface plus the entropy of matter outside that surface, including the matter of including the quantum fields, the entropy of quantum fields. But it's the area of a surface, and we have to pick the surface, and it's a surface that is, roughly speaking, the smallest. Roughly speaking, makes this smallest. So that's what this minimum is. More precisely, I don't want to get into the details. There is a reason it's really an extremal. There is an extremality condition, because if you move it in the time direction, it needs to be a maximum along the time direction and a minimum in the space directions. Now, conceptually, what you're supposed to do is the following. So you start with a surface that surrounds the black hole. So this green surface would be a two-sphere that surrounds the black hole. And then you compute the area of this two-sphere and the entropy of the quantum fields outside. And then you move this surface, you can move it to the horizon or even inside the horizon in such a way as to minimize this quantity. Once you found the minimum, then the value of the area plus the entropy, that gives you the actual fine-grained gravitational entropy. Now, so let me show you some examples of how this works. So let's again consider the picture of the black hole that forms from collapse. So this again is the space-time picture. This purple surface was like this ring that we had around the black hole that we are replacing by a quantum system. A two-sphere that surrounds the black hole at some moment in time looks here like a dot. So it's localized it's sitting at some radial position. That's why it's localized in the horizontal direction. But it also sits at some particular time, and that's why it's localized in the vertical direction. So now we're supposed to take this surface and find, we can move it inside. And here you can see that if you move it inside, you can decrease the area, okay, of the surface. And it turns out that for this problem, if you go here to 0, so that it has zero size, the area is 0, then that will be the minimum. And if you do that, then the total entropy will just come from the entropy of the star, because this whole region is left outside the surface. And the entropy of the star will be the entropy, the fine-grained entropy of this problem. Notice that in this system, the entropy, the fine-grained entropy is just the entropy of the initial star. The entropy doesn't change. On the other hand, the thermodynamic entropy changed because the area of the horizon grows from 0 to the non-zero final value of the black hole. So this is a clear case where there is a difference between the two. This gravitational entropy formula is giving the expected answer that we expect for a quantum system that is evolving sort of autonomously without coupling to the exterior. So here we are following here the rapid collapse before significant amount of Hawking radiation was emitted to the system. So you can approximate the system as a system evolving isolated from the rest. And so under such evolution, the fine-grained entropy should not change. Now, in the case of the Schwarzschild wormhole or the full solution, if we start from the geometry of this the geometry of this blue slice looks like a three-dimensional Euclidean space. And as we shrink, we have a two-sphere that is shrinking, and it reaches a minimum size here, and then it starts expanding again here. So when we try to find the minimal area surface, that surface will be here, and the area will be actually equal to the area of the horizon. So for this system, the entropy, this fine-grained entropy, is actually equal to the area of the horizon. So we saw two cases. The previous case was much smaller than the area. In this case, it's equal to the area, and there are also some intermediate cases. Now, you should be surprised by the claim that there is a formula for the fine-grained entropy, that there is a simple formula for, relatively simple formula for the fine-grained entropy, because that's not common in hydrodynamics, for example. If you thought that maybe gravity is a bit like hydrodynamics, this is not what's happening here. Now, it's useful for what follows to define a certain region of space-time that for historical reasons it was called the entanglement wedge. And it's the region, we keep track of the region swept by the surface as it tries to extremize the entropy. And the region outside the surface then will be called the entanglement wedge. So let me just give you some examples to see how this works. So we start from this imaginary surface we have around the black hole, and then we have the trial area, the trial surface that we are moving in order to minimize the entropy. And we keep track of this region in between. That's part of this entanglement wedge. And so, for example, when we go from here to the horizon, we sweep this whole region. And then the whole region of space-time that you can define by considering initial value data on this region, that's the entanglement wedge. So it looks a bit like a wedge, and that's why it's called entanglement wedge. It's called entanglement because this entropy is sometimes called entanglement entropy, this quantum entropy. Now, for a black hole from collapse, the same prescription will give you that the entanglement wedge is this whole region inside the black hole. Now, we saw that there was a quantum system that describes the black hole as seen from the outside. And one question you might have is, how much of the space-time does this quantum system describe? Does it describe only the outside, maybe also a portion of the inside? And if it describes a portion of the inside, which portion? And so we'll answer this question by introducing a new hypothesis, which goes by the name of entanglement wedge reconstruction hypothesis. So it basically says that the quantum system describes everything that is included in the entanglement wedge. So that's the reason for discussing the entanglement wedge. Now, by describes, we mean that we can recover the state of a probe qubit inside this region. This recovery is state dependent and has some similarities to quantum error correction. And there are many consistency checks of this picture. Now, the usual general relativity would tell you that you can only, from the outside, you can only see everything that is outside the horizon. So you cannot get any information from anything that is inside the horizon. And the idea is that this is what would happen if you do simple observations. So the new statement is that if you do arbitrarily complex operations, very complex observations outside, with looking at the Hawking radiation outside the black hole and looking at the states of quantum fields, etc., then you would see everything that is outside this minimal surface, this minimal surface that appears when you compute the entropy. In other words, you would see everything that is in the entanglement wedge. And by using this, this hypothesis, we see that many of these apparent paradoxes are removed. So for example, this paradox of the bag of gold, apparent paradox. So we had these spacetimes, whose spatial sections look like this, and we can have two possibilities. So we could have a situation where this closed universe contains very little entropy, or one in which it contains a lot of entropy. Now, if it contains very little entropy, then the entanglement wedge could include this whole closed universe. If it includes a lot of entropy, then it's convenient to put a surface here with non-zero area, and the entanglement wedge will be smaller, and will only cover the outside. So somehow this this combination of the the entropy formula together with the entanglement wedge reconstruction sort of ensures that you can never have a situation where the entropy, where you have more entropy than you can describe using the quantum system. And now we'll discuss the main example, which is the geometry of an evaporating black hole that was made from collapse. Now, if you have an old black hole, so a black hole that's been evaporating for a while, so you have a lot of radiation outside, and there is the partners of Hawking radiation inside the black hole. Then at some very late time, the area of the horizon at this late time will be much smaller than the area of the horizon at early times. And it could, and also this region inside the black hole interior could be very, very big. So on this slice, the geometry and also the distribution of the entropy looks somewhat similar to that bag of gold example. So we have a narrow neck, which is the area of the horizon at these late times. And then we have a big bulge here, where we have a lot of entropy coming from all the partners of Hawking radiation. And so one naive candidate for the entanglement wedge would be to put the quantum extremal surface at the origin, as we had done before for a black hole that has just formed. And if we do that, then the entropy will be given by the area of the horizon plus the entropy of all the quantum fields here, which will be equal to the entropy of Hawking radiation, because these two are entangled with each other. So that will give us a very big answer for the entropy. And that was the naive minimal surface, but there is a better surface. There is a second extremal surface, which is very close to the horizon. And in this case, now the entanglement wedge, or the region we can in principle describe using the black hole degrees of freedom, will be much smaller. And very importantly, it does not include the black hole interior. And this was a very important realization that was found in a couple of years ago by Pennington in one paper, and Mary Engelhard, Maroff, and Maxwell in another paper. And this has two implications for all black holes. First is that the fine-grained entropy of the black hole is close to the thermodynamic entropy, and also that the quantum system describing the black hole describes only a portion of the interior. Remember that we had asked the question of whether the quantum system that describes the black hole describes all the interior or only a portion. And here we are saying that for an old black hole, it describes only a portion. Okay, and in this way, you get, if you follow the entropy, the fine-grained entropy of the black hole, from one surface you would get a result which is rising, and from the other surface you see a result going down. Now, we can apply similar ideas to measuring the entropy of radiation. Now, when you think about the entropy of radiation, the radiation appears to be in a mixed state. And why does it appear to be in a mixed state? Because it was entangled with the fields that were inside the black hole. And how do we know this? We know this through the evolution of gravity, because that's how we got the state. But this implies that we should use the gravity rules to compute the entropy. So even though the radiation lives in a region where gravity might not be important, very far from the black hole, you might have gathered it into a quantum computer and so on. Even though that's the case, because you obtain the state using gravity, you should use the rules of gravity to compute the fine-grained entropy. And when you use those rules, then you can say, well, you have to find this, this so-called entanglement wedge, or this minimal area surface. So if you just consider the radiation on its own, you'll get some large entropy. But this quantum, the gravitational entropy formula tells you that you should, in principle, include other regions and include the area of the other regions and the quantum entropy inside, and minimize over all possible choices of areas. So one thing we could do is we could include this whole region of the black hole interior. Now, by including this, we pay a price, which is the area, but we gain the fact that now the region involves both the Hawking partners and also the radiation, the Hawking radiation outside. And so the net entropy contribution from the Hawking radiation will be very small, because since the modes inside and outside are included in the region and they're entangled with each other in a pure state, they will not contribute to the entropy. So in this way, we get the small entropy, which is close to the area of this point, and this point is close to the horizon, so it's close to the area of the horizon or the thermodynamic entropy of the black hole. So in the end, we get the formula also for the radiation that follows this page curve. Now, you might think that this is just an accounting trick because we are just including this interior of the black hole. But this is the accounting rule that gravity instructs us to use. So this accounting rule was found and derived before it was applied to this problem. So it was found for other problems that I'm not discussing. Now, a more proper derivation of this accounting rule involves some wormholes. In fact, it involves some special type of wormholes called replica wormholes. I will not discuss them in detail. Instead, I will take the opportunity of discussing a more intuitive type of wormholes, and these replica wormholes are somewhat similar, and I'll try to discuss the connection later. Now, these wormholes are traversable wormholes, and so wormhole is some configuration where you sort of excise, you cut two little ball-shaped regions, and you connect them in some way. Now, the most popular of these wormholes, at least for science fiction authors, are situations where you cut out some regions and you connect them in such a way that the connection is much shorter than the exterior, or more precisely that it takes you much, they would allow you to travel almost instantly between distant points. And this is usually used in science fiction novels, it's used in movies and so on. And unfortunately, this type of wormholes would violate causality. And in fact, they are not allowed solutions if you think about general relativity and quantum fields. So you cannot solve Einstein's equations with this type of geometry if the matter is matter that follows the rules of quantum field theory. So the fact that these wormholes are not allowed is an interesting interplay between the equations of general relativity and quantum field theory. So I'm sorry for the science fiction fans, but those type of wormholes are not allowed. Now, recently it was found that there are some allowed traversable wormholes. And if they are such that the time it takes you to travel through them is bigger than the time it takes you to travel in the ambient space. So in that case, they're allowed to exist. And when I'm talking about the travel time through the wormhole, I'm talking about the travel time as seen by someone who is outside the wormhole. Now, these wormholes are quite interesting configurations that require a mixture of general relativity and quantum effects, such as Casimir energy. So you need to have some negative energy in this region of the wormhole. And this negative energy is possible because you essentially have a circle here that goes around the space-time, and quantum fields, quantum field theory, when you have a spatial circle, can develop a negative energy. And this negative energy is enough, or can be enough in certain circumstances, to form this traversable wormhole. Now, in fact, you can have fairly concrete solutions. So you don't need exotic matter. So the matter of the standard model is enough to produce these solutions. But in this way, we can get solutions where the whole wormhole configuration is very small, smaller than the smallest distances we can see today with our most powerful microscope, which is the LHC. And the reason that we only get this solution is that in order to make this negative energy large enough, we need to approximate the matter of the standard model as being massless. So, and so for very tiny distances, all the standard model fields are massless, and for that reason, you can find the solutions. I should emphasize that these are, of course, theoretical solutions. They are metastable and relatively long-lived, but they are fairly fragile, so they can easily turn into a pair of black holes. And they are not we think that they are not easy to make. Probably they're very difficult to make, and they look kind of close to magnetically charged black holes. So they are such that there is a magnetic field going around this solution. So they look a bit like magnetic monopoles that are connected to each other through this wormhole. One fun question you can ask is whether we can have a configuration where a person can travel. Could we, in principle, have a wormhole-like configuration where a person can travel? This is just a question for fun. So we asked this question, and it doesn't seem possible to do it with the matter of the standard model, but we seem to need some new type of matter. And we can postulate a peculiar type of dark sector that was previously proposed by Randall and Sundrum, which involves an extra dimension and can be viewed as adding to nature matter which is scale invariant. And using this, we could in principle have a wormhole a wormhole solution whose mouths are the size of the Earth, separated by 10,000 light years. And the travel time as seen from the outside will be about twice or longer than that, as it should be in order to not to violate causality. However, the travel time for someone going through the wormhole would be about less than a second. So the reason for this very big difference in times is related to the fact that when you are falling into this wormhole, you are accelerated to very high speeds. And in addition, you are moving in a region where the redshift factor is very small, and there is a slowing of clocks, and so the time perceived by someone going through the wormhole would be very small. Again, this is just a theoretical solution. And now, after these fun solutions, we return to the main topic of the replica wormholes that we were talking about. I said I wasn't going to discuss them, but let me just give you a little bit of a hint or a taste of what this is like. So the idea is that to recover the information you sent into the black hole, you should connect the radiation and make it interact with a complex quantum computer. And this quantum computer basically simulates in a second black hole that creates a wormhole connection to the black hole interior. And in this way, the information goes through this connection with the interior, from the interior of the original black hole to the quantum computer. So it's similar to these traversable wormholes we discussed with some science fiction applications. And this has been the subject of some recent papers. So in conclusions, we reviewed the thermodynamic black hole entropy. We described the fine-grained gravitational entropy formula. You should view this formula as a generalization of the Hawking-Bekenstein black hole formula. And we applied it to the computation of the entropy of Hawking radiation. A lot of what was discussed was originally found by thinking about aspects of ADS-CFT, which itself was derived using string theory, but you don't need to know anything about that, so you only need gravity to derive and talk about these formulas. And also, somewhat in passing, we mentioned some fun traversable wormhole configurations. And I should say that I'm in awe of how clever gravity is, that it can give us these interesting formulas that suggest that really gravity is consistent with quantum mechanics. In the future, we hope to be able to give a more explicit picture for the black hole microstates from the gravitational point of view. And we also would like to understand better what this is teaching us about the interior, and especially about the singularity. Okay, thank you.
Okay, thank you, Juan, for this fantastic colloquium. So then the room is open for questions. Then please raise your hand if you can. Any questions? So what is the role of the singularity in all this story? Then,
yeah, it's not playing any role, actually. So that's something, if you wish, it's disappointing, but it's what makes it work. I mean, If it had played
Right.
an important role, then since we don't know what GR says about this, yeah, but it's not playing any role. I should say that what does play a role is the interior. So it's important that these surfaces are inside the black hole, but not the singularity itself. Yeah.
Tom, please.
We
you
cannot
are
hear
still
you.
muted, Tom.
You're muted.
There.
Okay.
The essence of what you were saying, it seems like, is that you had to be kind of careful about two senses of the word entropy, depending on
Yes.
what point of view you took.
Yes.
It seems like one might encounter such paradoxes and such duality, two ways of interpreting an entropy, without them having to do with black holes, especially.
Right. Yes.
Like, I don't know, you can imagine ordinary matter having some degrees of freedom in it that normally you don't think about. Like, let's say the nuclear spin, we don't count that. We have a ball of gas.
Yes.
A bottle of gas.
Yeah.
Is there some way to phrase this in really concrete terms that we have seen an example of?
No, I don't think so. I think this is very unusual. Okay. What is unusual is not that the fine-grained entropy could be different than the coarse-grained entropy. That's usual. What is unusual is that there is a simple formula to compute the fine-grained entropy. That is what is unusual. And it's so the unusual thing is this gravitational entropy formula. I mean, it's already unusual that we had a formula for the entropy of a black hole, which was the area of the horizon. That's somewhat unusual because we would have thought that empty space doesn't have any entropy. So that was a bit unusual, but you could say, well, this might be like thermodynamics, where also if you have a fluid, you can assign it an entropy based on some other thermodynamic variables like its density or its temperature and so on. So that might not be too surprising. But I think you should be surprised by the claim that there is a formula for the fine-grained entropy. And it is the simplicity of this formula and the features of this formula that were running this show that were important for what we discussed.
Okay.
Yeah.
Okay, Craig.
And it goes, it's a notion of, it's an entropy formula that goes beyond the Hawking-Bekenstein formula. So now we have sort of two formulas. One is the area of the horizon, and the other is this fine-grained entropy formula or Ryuta-Kayanagi formula, which they are giving us two different notions of entropy, and we should use the latter for some of these problems.
Okay.
Yeah, so just kind of pursuing that same line of questioning. So, you know, naive entropy we're used to is just an extensive quantity. You can have a chunk of entropy in a certain volume of space, and they're kind of independent. This is also different because it's a non-local thing.
Right.
And I guess kind of the question is, you know, what are the lessons we should take away about the non-locality of quantum gravitational states, and how you extrapolate to?
Right. So, well, first about the non-locality of entropy. So this, or non-extensivity, this is related to the fact that to entanglement. So if you have an entangled system and you take one of them, it will have some entropy, and each of them individually will have some non-zero entropy. But if you take them together, it could have zero entropy. So the entropy of the sum could be smaller than, or the union of the two systems could be smaller than the entropy of each one individually. So that's one feature. Now, these formulas are also suggesting that the way we assign quantum systems to gravity, we assign, let's say, different portions of space-time to quantum systems is also somewhat non-local. So in this description, the interior of an old black hole was assigned to radiation. So it's part of the system of radiation. So the idea is that if you do measurements, very precise measurements of the radiation, you can extract what is in the interior. Somehow that interior is already contained in the radiation. So the map between space-time and the quantum variables is non-local.
So, Guru Lakshmi.
Thanks for the nice talk. So while describing the old evaporating black hole, you mentioned that there are like two extremal surfaces. One is deep inside the black hole and the other is near the horizon.
Yes.
And yeah, so both of them have the minimal entropy. Does that give any insight on how the black hole interior should be and what kind of matter fields will be there?
Yeah,
like,
what this is how to divide so the idea is that we've divided the exterior of the black hole into the quantum system, right? What we were calling the quantum system that describes the black hole, and the radiation that is outside, right? So these are two quantum systems. And what these formulas are is they are partitioning the whole space-time and saying that some portions of the space-time are described by one quantum system and other portions are described by the other quantum system. What was surprising is that the interior is, according to this division, the interior is being described by the radiation and not by the quantum system describes the black hole. Okay, maybe I'll show this picture again. Can you still see the screen?
No.
No? Okay.
So there's no insight on that, right?
You can share it again, maybe.
I can share it again. Okay, let's see.
Yeah.
Yeah, so I showed this portion, right?
Mm-hmm. Yeah.
Now, part of what makes the statement I'm making confusing is it's a problem of language, okay?
Okay.
There are two things we can mean by a black hole. By a black hole, you can mean this whole space-time region, right?
Yeah.
Or by a black hole, you can mean some object I'm looking at from the outside, okay? And there is one thing you can talk about, which is the quantum system that describes this object from the outside, okay?
Okay.
That quantum system describes only this little portion here of the space-time. The quantum system that we were talking about describing the black hole, only this portion. The idea is that the radiation system describes both this region of space-time and also this whole black hole interior, okay? So what is here, this region of space-time is actually being described by radiation, should be viewed as part of radiation. So in our language, we were saying that this is the interior of the black hole, so it has to be part of the black hole degrees of freedom, but the idea is that they are not. They are not described by the degrees of freedom that are counted by the black hole entropy, for example.
All right. Okay. But there was another extremal surface that was just at the singularity, right? Deep inside.
Yes, yes.
So we don't consider that into account here?
Yeah, so another possibility, this is another candidate extremal surface, but if you remember the formula said that we should take the minimum one, the one that has the least entropy.
Right,
and,
so that was only the one near the horizon. Okay.
Yes, and if we took this one, that will have higher entropy, so it's not the one with the minimal entropy. So the correct one is the one with the minimal entropy, which was what gave this picture.
Right.
The radiation includes this system.
Okay, thank you.
Yeah, sure. Yeah.
Daniel.
Yeah, hi. Thank you for the beautiful talk. And you know, you mentioned science fiction. Maybe this question is in that direction, but I'm just wondering, you know, is there any sort of observational evidence in the foreseeable future, any sort of test that you would be, you know, excited about, that, you know, we could do even indirectly? You know, I'm thinking LIGO and strong field. And is there anything, you know, that sheds light on these sorts of questions that we can do in even long-term future?
Right, right. Well, the type of experiments that I'm most optimistic about and that people are pursuing are experiments for kind of analog systems. So this the type of correlations and entanglement that you get for these traversable wormholes, you can create them in systems in the lab, and that systems of strongly interacting quantum particles. And there are features of how information can travel between these two systems that is similar to how they travel in these black holes. So some detailed formulas. And I think those are the type of experiments that I find most realizable in the near future. They are not experiments that are probing our four-dimensional quantum gravity. They are experiments probing sort of analog gravity, if you wish, or gravity that would emerge there would be special two-dimensional gravity systems that emerge from these strongly interacting quantum systems.
And these systems allow you to specifically ask about entropy in a similar way?
Yes. The systems are called the Sashdev-Yeki-Tayev model. So it's the simplest systems involve interacting Majorana fermions. And they have features very similar to these traversable wormholes. In fact, these solutions that I was discussing here, they were first found in those analog systems, and then generalized to 4 dimensions. So there is a very close connection between the two. I could go on and on. I mean, what happens is that when these wormholes are very long, these wormholes are closely related to near extrema black holes, and near extrema black holes have an emergent scaling symmetry with a particular pattern of soft breaking, particular pattern of breaking of the system of symmetry of the system. And that pattern of symmetry breaking is present both in this black hole sort of 4D gravity solutions, as well as in these strongly interacting quantum systems we were discussing. And it's that which could be probed in experiments. Now, we might be lucky. So we might be lucky, for example, if small magnetic black holes existed. So then you could collect these small magnetic black holes and perhaps form these wormholes. Or maybe they can form perhaps in some way. But for that, you have to be pretty lucky. So there is no, the mechanisms for forming small magnetically charged black holes are somewhat artificial. I mean, they are not the most natural situations you find in inflation. I mean, it can exist, but it's a contrived inflationary mechanism.
Right. Yeah, that's harder. Yeah, thanks.
Okay, Edward.
Hi, I just had a quick question as to why one should maybe expect such a simple expression for the fine-grained entropy. Like, shouldn't I expect maybe a whole power series G Newton, and sort of S matter is just sort of the first correction to the area term?
Yes, that's correct. Yeah, these expressions are the leading. You are absolutely right, and these expressions are the leading contributions. But these expressions are the important contributions for the problems that we discussed. So we expect that the higher orders in G Newton for the situations that we explicitly discussed are not important.
Thank you.
Yeah.
Henry?
I was interested in how long it took for the radiation expressing the state inside of the, sorry, you call it the entanglement window or something like that. It took to like exit the black hole, or like whether that happened as a homogeneous process or like.
Yeah, so when we draw this diagram, we say that the information here is in principle contained in the radiation. It's contained, but not in a simple way. So now this happens when the black hole is old, that is, roughly speaking, let's say halfway through the evaporation of the black hole. I'm not sure if that's the question you were asking, but if you wanted to actually extract this information, you will have to do a complicated operation on the radiation. And your question can be interpreted as how long does this operation take? So that's supposed to be a very complex operation that could take an exponentially long time.
But in terms of like measuring the things that you would need to do the operation on, the complex set of measurements you would need to take,
Yes.
they would be in line with the the evolution inside of this area, but at a like later time than, or I guess it's difficult to talk about time, but
yeah, well,
that
yeah,
green area represents the
yeah,
area of space-time where you need to take all of the measurements, and that
yeah.
would completely represent the
Here
state.
the idea is you collect this, the state of radiation, you put it in a quantum computer, right? So you have to do a quantum operation, and this quantum operation will take you exponentially long time. It's exponentially complex. It's very complex operation, and so that's I'm not sure if that's answering your question.
Yes, thank you.
Clay, maybe the last question.
Okay. So in your opinion, what remains of the black hole information problem, if anything?
Well, I think I think the most important, well, or for me, the most interesting aspect of the black holes is to understand what happens with the singularity. And I think this is the most interesting aspect because the singularity shows sort of the opposite of the Big Bang singularity. And if we understood how to think about the black hole singularity, we would understand how to think about the Big Bang singularity. And that's something that is not understood. So I think.
But do you think that that problem can be, I mean, this problem was almost solved by semi-classical general relativity.
Yes. This problem was solved by semi-classical general relativity. And well, the other problem, it looks like it cannot be solved by semi-classical general relativity, but it was also thought in the past that you could not solve this problem using semi-classical general relativity. I mean, if you ask me, I would also say that the problem of singularity cannot be solved by semi-classical general relativity. But if you had asked me about this problem a few years ago, I would also have told you that it cannot be solved by semi-classical general relativity. But yeah, so if you ask me now, I'd say, yeah, the singularity will need something more, but we have to discover what it is.
I have a comment. So that somebody was asking about getting a copy of your talk.
Okay, yeah, I'll send you one.
Very good, thank you.
This is also recorded.
This is recorded, very good. But it would be nice to have a copy so one can follow it. Then. Okay, Watson, the really last question. Then. So we have had one for a long time already. No, you are muted. You are muted, Watson.
Yeah, maybe a naive question, but so the radiation outside is entangled with stuff on the inside of the black hole, right? So when you make a measurement of that radiation, like like does it like it should project the state of the black hole as well, right?
Yes. So for example, if you
how does it change it?
Yeah, well, in the semi-classical description, what is happening is simply that when you measure the radiation here, let's say initially it's entangled with the right. So here you measure, it's like a spin that is in the plus C component. Then here the partners would be, well, in the minus. I mean, it would project it in the same way that it is projected when you have entangled states. So once you project the whole radiation into a set of, let's say, plus minus, etc., you have the same type of projection in the black hole interior.
But there's no issue with that, like that doesn't. Like,
no, there isn't any issue. I mean, it's consistent with this picture. Yeah.
And after the measurements, you said that you can use the results of the measurements with the quantum computer to make a wormhole, right?
Yeah.
Well, how does that work?
No, not after the measurement. So the measurement can change the position of the quantum extremal surface. So you have to do a quantum operation without measuring. You have to do coherent operation on the qubits.
I see.
Yeah. Now, if you measure the radiation, then you create a special state here, and then the quantum extremal surface might move all the way to the left, and you lose access to this left system from the radiation.
I see.
In the same way that if you have a quantum state that is entangled and you measure just one of them, you might lose some access to information that was in the other one.
Okay, so then I don't see any other questions. So then we thank Juan again for this fantastic talk. Then thank you, Juan.
Okay, well, thank you, and best wishes to everyone.
Thank you.
Thank
Thank you
you.
very much. Beautiful.